evolution of our solar system is one of the most fascinating and enduring mysteries in science. For centuries, scientists have developed a variety of theories to explain how the sun, planets, moons, and other celestial bodies came into existence. In this video, we'll take a journey through the most important theories that have shaped our understanding of the solar system's origins. The story of our solar system begins about 4.6 billion years ago, when a vast cloud of gas and dust, known as a solar nebula, began to collapse under its own gravity. But how did this cloud form, and how did it evolve into the system we see today? Let's explore some of the leading theories. The most widely accepted theory is the nebular hypothesis, first proposed by the German philosopher and scientist Immanuel Kant in the 18th century, and later refined by Pierre-Simon Laplace. According to this theory, the solar system began as a massive cloud of gas and dust. Over time, this cloud began to collapse under gravity, and as it did, it spun faster and flattened into a disk. In the center of this disk, the sun formed as gravity pulled the material together. As the cloud cooled, particles collided and stuck together, gradually forming larger bodies. These clumps of matter eventually became the planets, moons, asteroids, and comets that we see today. This theory explains why the planets and sun all rotate in the same direction, and why most of the planets are roughly aligned along the same orbit. A modern refinement of the nebular hypothesis is the solar nebula theory, or the solar nebula disk model. This theory suggests that the collapse of the solar nebula was triggered by an external shockwave, perhaps from a nearby supernova, or the gravitational influence of a passing star. This shockwave could have caused the nebula to collapse faster, forming a rotating disk of gas and dust. The heat and pressure in the center of the disk caused the sun to ignite, while the other regions cooled and solidified. The theory also accounts for the distribution of elements in the solar system. Lighter elements like hydrogen and helium remain in the outer regions, while heavier elements like iron and nickel concentrated near the sun, forming the rocky planets. An offshoot of the nebular hypothesis is the protoplanet hypothesis. This theory proposes that as the nebula cooled, it formed solid particles that collided and stuck together, growing into planetesimals, small rocky bodies. Some of these planetesimals continued to collide, merging into larger objects known as protoplanets. These protoplanets eventually grew large enough to become the planets we know today. This theory helps explain why some planets are rocky and dense, like Earth and Mars, while others, like Jupiter and Saturn, are composed mostly of gases. It also suggests that other planets formed in the colder regions of the nebula, where icy materials could condense, while the inner planets formed closer to the sun, where only metals and silicates could solidify.